maybe you can try to present it again. Yeah, to everyone else, welcome to our evening session. We have, it's my great honor to introduce Mikhail Belkin, who's a professor at Ohio State University. Yeah, this is perfect. And he's going to talk about generalization and optimization, and I'll let him introduce himself a bit better and then go into the slides.
Thank you very much, Razvan. Great to be here virtually. I'm actually moving now. I will be at UCSD at the new Center for Data Science from this summer, in fact.
Perfect.
Yeah. So what I've been very interested in the last few years, we have seen a lot of real, pretty amazing progress in deep learning. Is that problems that we couldn't solve before now seems, or couldn't solve well before, I should say, are now easily solvable by doing, using various deep neural networks. And we have observed a lot of empirical phenomena, which are just very hard to reconcile with existing theory. And then that has been my interest in the last few years. And I think now we have at least some beginning understanding of what's going on, and we can start to really build a theoretical foundation for the phenomena of deep learning. And my hope is that this foundation will also help us to develop practical methods as well. Okay, now I am going to describe some aspects of this understanding that we have, and this is this is still a developing view, and this is my view. So you have to make your own judgment, of course. But I think that the picture is becoming coherent. And well, as I said, deep neural network, they're objects like this. Can you see my my pointer when I move pointer here?
Yes, we can.
Okay, good. So I can point as this. The deep neural networks are objects like this, and these are very complex architectures with multiple moving parts. There are activation functions, there are optimization method, architectures, lots and lots of different things. And the question from a theory point of view is that, well, should we build those things? Well, that's what a practitioner would say, right? Let's just build them, make them more complicated to improve performance. Or should we take them apart? And to understand the things, we actually have to take them apart. We have to simplify. And sort of the key question is, well, what lessons can we learn from that? And the key lesson that I was going to describe in this talk is that we need theoretical foundation. We need to rethink theoretical foundation for machine learning, both in terms of optimization and generalization. And I will start with generalization. So the classical paradigm, as I'm sure everybody knows, in supervised machine learning is the following. You have xi, yi. Xi are features and yi is a label. You can just assume they're binary label. And based on this data, you want to construct a function from features to label that generalizes to new data that you haven't seen before, right? And how do you think about this new data? Well, the standard statistical assumption is that the new data, well, all of the data are sampled from a certain probability distribution. And if you believe that this is correct assumption, at least, it's reasonable simplification of what is happening, then the best you can do is to choose your function f star as the argmin of the expectation of unseen data of a certain loss function. So this is the best you can possibly do. Now, what do we actually do in machine learning? Well, what we use what's called empirical risk minimization. And almost, well, I don't know, almost all, a lot of theory is based on this type of procedure. And I'm kind of posing it very abstractly, but usually it's done algorithmically. And the idea is that you want to minimize the empirical risk. What's the empirical risk? It's a risk over the training data, right? You have the loss, for example, square loss or hinge loss or cross entropy loss over your data points, xi, yi's. And you minimize this loss over some class of functions H. For example, neural networks of a certain architecture, right? So you choose neural networks which perform best on your training data. So now, if you look at this empirical risk minimization and you compare it to the optimal, right, you see something like that. So goal of machine learning is argmin over all functions of expected loss of unseen data. Goal of empirical risk minimization, which is your procedure, is to find the minimum over some class of functions, much more narrow than all functions, usually, of the training loss, right? So one is test loss, unseen data is kind of the test set, and one is the training loss. And the way analysis, classical analysis, I should point out, work is to connect those two. And I'm kind of going over the classical analysis, but going over the classical analysis here, it will become clear what's broken and what needs to be fixed. So how do we do this? Well, the sort of most standard description of this goes to Wapnick, and he described it quite nicely in his book on statistical learning theory. The theory of induction, as he calls it, is based on the uniform law of large numbers, and effective methods of inference must include capacity control. So I'm going to unpack those notions now and point out how this classical analysis works. So first, what is uniform law of large numbers? Actually, uniform law of numbers is very easy. I mean, that it can be complex mathematically, but it's kind of easy to understand. It is simply saying that empirical loss for any function in this H, this space of function where we do empirical risk minimization, this kind of class of functions H, approximate the expected loss of F. So what you see on the training test, you will see something on the test set. That's uniform law of large numbers. And capacity control simply means that H contains functions that are close to optimal. That's it. Now, it is actually not difficult to see that if you have 1 and 2, then the optimal that you get by running your empirical risk minimization is not very far from the actually best possible. I'll unpack this a little bit more. I'll go a little bit deeper into unpacking this. And let me unpack this uniform law of large numbers. Those are based on what you might call WYSIWYG bounds. WYSIWYG stands for is what you get. And there are many, many types of this bound, and there is some really nice mathematics associated to them. And the way it works is follows. On the left, you have the expected risk, which is what you get in the future. On the right, you have the empirical risk, which is what you see, this term, and some sort of term associated to function complexity. Class of function complexity, I should say. And there are different bounds, which depending on how exactly you set up the bound. Now, this bound is essentially said that what you see, which is empirical risk, is what you get, which is expected risk, right? Expected risk is bounded by the empirical risk. Now, how does this work? This is a very nice illustration from the Wapnick's book. And basically, it says that as you are changing the richness of the class of functions, so the x-axis here, H, is how rich your class of function is. So as you add more and more function, to your class of functions, your empirical risk goes down, right? Because you can fit data better and better with more functions. But if you look at the previous slide, here you see that this remainder term goes up. So empirical risk goes down, but as your function becomes richer, the C increases. And you have what he calls the confidence interval, which is the bound, which goes up. And the sum of those two things has this U-shaped curve. And the idea is that the bottom of the U is optimal. The way this is represented in sort of more commonly is basically sometimes called bias variance trade-off. And it's represented like this. This is kind of a heuristical representation of the previous slide. You have as you increase model complexity, your training loss goes down, your test loss initially goes down, and then it goes up again. And what we know is that on the left, this is underfitting, on the right, this is overfitting, and the goal is to find the sweet spot, which is the bottom of this U. A kind of corollary of that is that the model with zero training error overfits. The training data will typically generalize poorly. This is some sort of common wisdom. Now, I have described this quite carefully because what I'm going to show now is that this type of thinking is actually problematic. And this has been, I should point out zero training error, we call it interpolation. And let me give you the following example first, because that I think shows quite nicely what is problematic about this whole paradigm. And this is from Zhang et al. 2017. They trained a neural network on CFAR10, and they trained it to have 100% train accuracy. And you can see that normally that would be considered overfitted, but also you see that the test accuracy is actually not so bad. It's about, almost 90%. Now, on its own, this does not directly invalidate ARM theory and uniform bounds. But let me give you one of experiments which we did with my students, Siwan Bai and Suvik Vandal, which kind of shows what the problem is. And here, let me describe this diagram. So what you have on the x-axis, you have label noise. And what do I mean by label noise? We take MNIST, this is for MNIST, and we randomize some of the labels. So for example, 10, 20, 30, and so on, 60, 70% of the labels just becomes random. So when you randomize, say, it's a 10 class classifier, so even if you randomize half of the labels, there is still information there. But it becomes extremely noisy data set. And you can see here that as you're randomizing more and more, the best possible predictor is this green line. Because you can never predict labels which are random. So if your 50% labels are random, you're, just slightly less than 50%. The best classifier can do just a little bit better than 50%. Because sometimes randomness gives you the right answer just by chance. So this green line is absolute best possible, but of course it's unachievable. It's a theoretical lower bound. But what we see is that the red line, let me just remove, this is some sort of kernel machine. The red line actually is not very far from this green one. And I should point out that random guess will give me 90%. So now, what is this red line? It's basically a kernel machine, but neural network does something quite similar, which is trained to have zero training loss. And by loss, I mean square loss here. So it fits my data exactly. And now you can see how remarkable this phenomenon is that even with 60 or 70% label noise, I'm fitting this very, very noisy data exactly. And yet my test prediction is only a little bit worse than the green line, which is absolutely best possible. So I'm fitting very noisy data and I'm not paying for it. I'm not overfitting. Or if I'm overfitting, I'm just overfitting a little bit. and certainly very far from random. So this directly contradicts to the bounds that we had before. Why? Well, let's think about those bounds. We have the test loss on the left, we have the training loss on the right, and we have the model complexity. Now, when my training loss is 0, right? I have training loss, which is 0, test loss, which is not 0, and then I have model complexity now. So yeah, sure, this model complexity loss, it can be non-zero, but the problem is that there is no mechanism for this loss for the model complexity term or function complexity term to be predictive of the test loss directly. Why? Well, let's think about this diagram one more time. So you see, here is the problem. Let's look at this again, right? Training loss is 0, so test loss is less than this. So if I want to give non-trivial result, that means that the test loss better be smaller than 1, right? Because otherwise, okay, I know that if it's accuracy, right? Accuracy is always less than 1. So having accuracy less than 2 is a very boring bound. It's not useful. It's tautological, you might say. It always holds. Now, well, let's look at this. What does it mean that this bound must be non-trivial, right? If I want some sort of non-trivial bound, well, it better give me something which is bigger than the green line. Because if it's smaller than the green line, it's wrong, right? Nothing is better than the green line. That's a theoretical lower bound. It's a base optimal. So for that, it has to be bigger than 0.7, right? If you look here. On the other hand, it better be bigger, smaller than 0.9, because 0.9 is a random guess. And if I'm above random guess, it's useless. So this is what we get. For this bound to be correct, it needs to be bigger than 0.7. For this bound to be useful, it has to be smaller than 0.9. And we better have it as n becomes large. There is a problem. First, a constant in O star needs to be exact. And usually it has log factors and all sorts of stuff in there. So there are really no bounds like that. And conceptually, I think, and more troubling is how would this quantity even know about the base risk? How does it know that it has to be bigger than 0.7? Because somehow it has to look in great detail at the function. So I think it is fair to summarize that there are no bounds like that, and it is hard to expect that bound is useful. Now, I should point out that this is not so this zero loss kind of phenomenon. This is, you might think, okay, this is some sort of weird marginal phenomenon, but no, actually, this is the way people use deep learning. And I think Ruslan, in his tutorial 3 years ago, had a very nice description of it. He said the best way to solve the problem from a practical standpoint is that you build a big system, you have 0 training error. So that's actually the step toward building neural networks. And well, it's not the last step. I should point out that he didn't say that you stop at this point. But the interesting thing is that you already get good performance even if you don't do anything else, as we have seen. But you can increase performance from there, but by adding regularizations and other things. But if you just do this, you're already kind of. Now, I should point out that there has been historical recognition of this problem, like Jan LeCun in actually a bunch of talks, he would say something like deep learning breaks some basic rules of statistics. Goes much further back than that. Leo Breiman wrote a nice note 25 years ago, as a matter of fact, and one he poses several questions. The first one of those is, why don't heavily parameterized neural network overfit the data? And I should point out that this was also the question addressed in the boosting of the margin paper by Rob Shapiro, Freud, Peter Bartlett, and Wilson Lee. And they point out that the test error of the hypothesis does not increase as its size becomes larger. And they propose an explanation based on the margin, but unfortunately, the margin cannot be the whole story because margin bounds are still of the same. What you see is what you get for. So here is a kind of summary of empirical finding that the goal of optimization, which is minimizing empirical loss, unexpectedly, and I think fully justified here to use the word unexpected, since this clearly contradicts what's written, in well-known books, unexpectedly aligns with goal of machine learning, which is minimizing the expected loss. Okay. Now, here is the key lesson we can extract from this, is that the new theory of induction, the theory of induction we want, and the theory of induction which would explain some of the phenomena that we observe in deep learning, but also not just in deep learning, like what I showed was a kernel machine, right? It wasn't even deep learning. Cannot be based on uniform loss of large numbers with capacity control. We need something else. And the question then is where next? And I'll give some ideas on where to go next. These are not yet in the form of a complete theory, but I think they're highly suggestive of what to look for. You will see. Now, I should maybe very quickly go over the what kind of analysis we have. And the analysis which are compatible with interpolations are not many. And if you look at the standard WYSIWYG bounds, basically none of them work. And things like algorithmic stability, regularization types analysis have issues. Algorithmic stability and VC dimension really don't work because they're WYSIWYG bound. Regularization type analysis don't necessarily have this, but really we don't have any good bounds like that. But there is one actual example of something that works, and this is one nearest neighbor. And one nearest neighbor, well, so you have your data, right? Given a new data point, you simply choose the exemplar which is closest to your test point. That's it. And it works. It's a practical method. It's analyzed theoretically, right? And you have a sharp performance guarantee that the performance of one nearest neighbor is twice the base rate. It's due to covering hard. Very classical result. Now, the cool thing about it is that the analysis is not based on complexity bound. And we estimate the expected loss directly. We don't estimate the gap between the empirical loss and the test loss, as in most WYSIWYG bounds. Now, let me very briefly describe a class of methods which actually can be shown to be statistically optimal. So one nearest neighbor, of course, is not statistically optimal. It's not even unbiased, right? It gets twice the base error. But you can actually find something which is consistent and converges to the optimal classifier. And in fact, it's even stronger statistical optimality. And it's kind of very similar in spirit to one nearest neighbor. And I should point out this is joint work with Daniel Su and Partha Mitra, and then there is a follow-up on statistical optimality specifically with Sasha Raklin and Sasha Tsibakov. So here is a scheme. You use a kernel, and this is actually closely related to something called Shepard's interpolation. You use a kernel, which is an inverse distance. So the easiest way to think about it is k of x XIX is 1 divided by the distance between x and xi. So you can see it kind of becomes singular. When x is equal to xi, it becomes infinite. Well, the long story short, you can write a function like that. And this is a sort of classical estimator, but we're using this unusual kernel. And it turns out that the schemes, and I'm hiding a bunch of details under the carpet, but they can be shown under some conditions to be, under some choice of kernel, I should say, to be consistent. They converge to the base optimal. And moreover, they, in fact, even statistically minimax optimal. And I don't want to describe the theory too much, but let's just look at the picture a little bit, and you'll see how weird what was happening is, right? So what do I have in the picture? Those little circles are my data points. And the optimal classifier is this blue line. And how do I know? Actually, it's regression, the optimal regression. And how do I know it's optimal? It's because the data is sampled from this blue line plus noise. So if you know a priori best prediction, you just predict this blue line. Now, if you do linear regression, you probably do something reasonable, not too far from the blue line. But let's look at what one of those predictors does. You see, you can kind of see that at every data point, it fits the data point exactly. It kind of spikes here. So you have this extremely spiky function. And you can say, well, okay, this is completely crazy because I'm fitting the noise. But here is interesting observation, is that even though it fits this noise exactly, on average, the red curve is not actually too far from the blue line. That's exactly the phenomenon that we're dealing with here. That's this optimality. So even though we're fitting the noise, we're not paying for it because somehow fitting the noise is too localized. And an interesting kind of side effect of this is adversarial examples. Let me just very briefly say a couple of words about this. What's an adversarial example? Adversarial example, right? When you take an image, it's classified as, well, it's a dog, right? We see it. It's classified as a dog by, say, a neural net. You can add a little bit of noise, which you cannot really see because it's very small. And suddenly, the neural net classifies us as an ostrich. Okay, well, to us, at least, it's indistinguishable. Those two images are indistinguishable. Well, it turns out that if you believe in the story of interpolation that I discussed, such adversarial examples will actually be asymptotically dense, assuming the labels are not deterministic. So you will always have adversarial examples. I don't know, this is not the only mechanism. I believe this is not the only mechanism by which adversarial examples are formed. There are other things. But I think what is nice here is that the theory directly compatible or suggests things that we're observing in practice. Okay, now I'm going to slightly take a step back and say, like, okay, so what did I discuss so far? First, I showed that interpolation is empirically effective, right, by giving us some examples. Second, I discussed that the theory of interpolation cannot be based on uniform bound. And third, I showed that interpolation by certain methods can be statistically valid, right? This kind of weird kernel nearest neighbor type of method. Now, I mean, you can sort of reasonable question would be, there is a mismatch between A and C. I show that interpolation is effective for things like neural networks and kernel method. What I analyzed in C is methods which are completely of different types and not those which are typically used in practice. So what is going on? And I think the key question is, well, first, dependence on generalization of model complexity, which is normally this U curve. And second, the role of optimization. And let me discuss this. So first, I would like to sort of directly address the question of model complexity. So as you remember, what I have on the left is this kind of classical U-shaped curve. On the left, you have underfitting, and on the right, you have overfitting. And in the middle, you have the optimal solution, the sweet spot. But the question is, what happens if you keep increasing complexity of H? And classically, it doesn't make sense, right? Because if you don't have, you know, once you hit zero loss, how can you increase complexity anymore? But then you realize, well, yeah, you can, because with something like a neural network, you just add some more hidden units, right? Nothing prevents you from having as many hidden units as you want. It has nothing to do with your data size, right? I think what is very nice about deep network, which is, it's not just true for deep network, but in neural network is much more clear, is that the architecture of the neural network is completely decoupled from your data. That's not necessarily true for things like linear classifiers, right? Somehow architecture the data somehow together. In any case, be it as it may, if you increase complexity of H past this interpolation threshold, past the point where the trading risk is zero, loss risk, I use it interchangeably, we see the second descent. It starts, the test risk, the generalization risk starts improving. And this is what we call modern interpolating regime. So we call this double descent curve because you kind of have this classical U. So you have this initial descent, then it goes up. And then there is a second descent when it becomes lower in this modern interpolating regime as complexity of H increases. And usually, but not always, it just keeps increasing indefinitely to infinity. It keeps decreasing, I'm sorry. Now, of course, it doesn't decrease to zero. And a reasonable question, well, does it decrease below the bottom of the U or does it stay above? So the way I drew here, it's slightly below, which seems to be the case in many practical applications, but not all. And in kind of in toy examples, you can choose those things either way. So you can be better or this point can be better. It really is data dependent, data and model dependent. Oh yeah, and I should say this is joint work with Daniel Su, Hugh on mine, Subik Mandel. Now, we have done quite a few empirical analysis. Neural networks, random forest, L2 loss, L2, it's a type of boosting, random value networks, many different architectures and different data sets. And this performance, this kind of phenomenon, this shape seems to be quite consistent. So we believe that this is, if not always happen, then it's quite general, it's quite ubiquitous. And I should point out that other people also observed this. There was Advani Sachs 2017, and this is for linear model, and Spiegler et al. 2018 for certain neural networks. And yeah, recently there was also work where they, by Nakira et al., where they trained a bunch of different kind of standard architecture, convolutional neural networks and other things. And they also consistently observed this. So this may look a little bit mysterious, right? Because why should it go down from this point? And what I would like to do, I would like to consider one very simple example when you can kind of visually see what is happening. And the effect is as follows. Let's take, so let me give you the setting first. Consider neural network with just in one dimension, with just one hidden layer of size L, okay? And I am choosing the first layer coefficients at random. So that means that my neural network has this form, and BJs are just random numbers, okay? CJs also. So that means that I'm just training alpha J, and the problem becomes simply linear regression, but it's training a neural network. Okay, let's now see what it looks like. And here is the first picture. And this is, I only have 3 random value features, so it's a neural network with 3 units. Okay, so my red points here are my data. Remember, they're one-dimensional. And the blue line is the output of a neural network, and you can see it kind of fits the data pretty reasonably. It's what you may call a standard parametric model type of fit. Now, let's increase the number of units. And I'm increasing them now to 30. And an interesting thing happens, right? When I have 30 random hidden units, I have a curve which fits my data perfectly, but the curve oscillates. This is classical overfitting, right? You don't expect this to generalize well because it kind of goes crazy. It goes up and down. And that's where the kind of classical theory would end, right? You say, okay, you have this is good fit on the left. On the right, this is overfit. And of course, I can do underfit, which would be just linear probably in this case. But let's increase the number of units to 3,000. And we see a remarkable thing happens. I see another curve which fits my data exactly, but now it is a nice smooth curve. So now you can say, well, which one is better, the one on the right or the one on the left? And the one is answer, I don't know. It depends on the data, right? But they both look reasonable, while the one in the middle looks bad. So you can see overfitting actually just happens in the middle. There is no overfitting on the left, and there is no overfitting on the right, only in the middle. Now, you can, maybe I'll go quickly over this. You can do the same thing with random Fourier features, and what you observe is the following, is that as you're increasing the number of features, so I'm increasing here the number of random Fourier features. I don't want to describe what exactly they are, but it's kind of similar to the units that I had before. It's a similar picture. You can see that you have the classical U-curve, then you get the second descent. So you have a very beautiful double descent curve here. But because it's for random Fourier features, this actually is the limit. I know the limiting point. And the limiting point is a kernel machine. And I actually know exactly the loss of the limiting point, which is this red line, which is about 47%. Oh yeah, you could say 47% is very bad. No, it's not so bad because there are like 30-something classes in this data set. 38, I think, something like that. And now you can ask, well, why does it go down here? And one way to think about it is to look at the norm of the solution, and we can actually compute the norm. And you see a remarkable thing, that the norm of the solution, it increases up to the interpolation threshold, which is at 10,000, these are thousands of features, and then it decreases again. And maybe the way you should think about it is the following, is that in this classical regime, right, I'm trading off my loss and somehow the complexity of the classifier. In the modern regime, there are many solutions which fit the data exactly, right? Because once I have more features than the number of data points, I have many solutions. But if I choose a solution with the smallest norm, I do actually pretty well. And what you see when you add more features, why does it make my prediction better? It is because when I have a lot of features, I have more freedom in choosing solutions with the smallest norm. So that's kind of the explanation for this. I'll generalize this a little bit, but that's kind of the explanation for why having more features is often better. Like, why does it go down after this point? And you can see why it's also worst here. So what is this threshold? The interpolation threshold is the first time when you have exactly the number of features to fit the data. So your number of features, in this case, it's equal to the number of data points. So you have exactly one solution. But this can be a really crappy solution because these features are not optimal and there is noise and so on. So if you have exactly one solution, it's very bad because you have no choice. But once you have many solutions like here, you choose the one with the smallest norm, and this is good. So that's how it works. The minimum norm solution somehow is good. And you can see that in the limit, it actually converges to the kernel machine with Gaussian kernel. It's the same here. And you can actually see that this kernel machine, which is essentially the same as solution with infinitely many features, provides best performance. So this is kind of a summary that more features is better approximation to the minimum norm solution. Now, maybe I'll skip this one. Now, you can show mathematically that the thing it happens, and there have been quite a bit of work in the last year, last year and a half on this, and really we now have a bunch of different models proving that this is indeed the case under at least some simple settings. And you can say, well, why is it like that for neural networks? And the honest answer, well, we don't have a good model for really complex neural networks, but there is a lot of evidence that this model kind of describe at least some sort of essential behavior of more complicated neural networks. Okay, so now I would like to point out something about empirical risk minimization and interpolation. And I would like to point out here that in classical empirical risk minimization, you minimize the loss on the training data, right? And what I described there is that you choose a solution which fits the training data exactly. And among all of those solutions, you choose the one which has the smallest norm. So this is kind of classical empirical risk minimization, and this is modern machine learning. You should really put modern machine learning in quotes because this is, in some sense, this is classical regression as well. But I think it's useful to think about it this way. And the interesting thing is that if you look at the surface, this looks very different, right? They kind of look like a different optimization problem. But the interesting thing that when you're doing something like gradient descent, at least for linear regression, you get either of those solutions for free. So gradient descent for linear regression in under-parameterized case will give you this. In over-parameterized case, it'll give you that. And that's it. You don't have to know which regime you are in if you don't know how to count the number of features somehow. So that very much looks like what's happening in deep learning because you don't really know how many features you have or what exactly is the space of features. You just do some process and it gives you a solution. So there is some sort of magic associated with it, gradient descent, stochastic gradient descent. Okay, now maybe I'll skip this. Let me kind of summarize. This is, you can think of it as a framework for modern machine learning. And it's a form of the Occam's razor, right? What does Occam's razor say? You should choose the simplest solution which describes your data. And what I've described is actually a very pure form of this, because what does it mean that you describe the data? That means that you interpolate, you fit the data exactly. What is the simplest solution? Well, if you think of norm somehow being important, then this would be a solution with the minimum norm, which interpolates the data. So if you think about the Occam's razor, this is exact instantiation of the Occam's razor. But instead of the norm, I prefer to say this is smoothness because, well, norm is not so general. It refers mostly to things like when you can define functional norm, but there are many averaging kind of processes where norms are not clear. So really, there are three ways to increase smoothness. There is explicit, by using this minimum norm. There is implicit by some sort of optimization, which we believe connects to some norm, but we don't necessarily know how or what norm it is. And there is averaging, where there is no norm, but if you average a bunch of non-smooth solutions, you increase smoothness. I didn't describe this in detail, but it's a very similar mechanism. Okay. I should finally note all of those coincides for kernel machines. Kernel machines somehow are special, because all of those things actually give you the same answer. Now, where is the interpolation threshold? If that here is, I just would like to point out one thing. If that interpolation threshold really, it's the number of parameters equal to the number of data times the number of classes. Strictly speaking, number of classes minus one. Doesn't matter. So for CFAR 10, when you have 50,000 data points and 10 classes, it's about 500,000 parameters. And most modern neural networks have more than that. So we are always over-parameterized there. For ImageNet, it's less clear, because ImageNet, you have 1 million data points and 1,000 classes, so you need 1 billion parameters. So you can kind of view as modern architectures being somehow close to the threshold, close to the interpolation threshold. and or even under the interpolation threshold. And that's why it looks like using various tricks like regularization and other things is particularly important, because you can get a very bad result here if you don't regularize properly. So I'm going to summarize the landscape of generalization very briefly, and then I want to say a few words about optimization. And actually, I'll take questions after this slide, and then I'll say something about optimization. So here is the landscape of generalization. On the left, you have this classical regime, the WYSIWYG bounds apply. On the right, you have this modern machine learning regime, and your generalization is based on inductive biases and functional smoothness, and we are finally starting to see analysis in the last year or two, which describe this. And finally, I should point out that overfitting now, we can really see overfitting is not just one thing. It's not that when you fit the data too well, the training data too well, you overfit. Overfitting is really a range, a band of parameters. That's maybe kind of one practical output of this, is that we can kind of go past overfitting. And yeah, I think this is a good time to stop and take some questions.
Okay, perfect. Let me share the questions. Can you see them?
Yeah, perfect.
First question.
I see the top three. Yeah.
Yes, perfect. Let's start with the first one. How would you explain the phenomena when the training loss is increasing, but the accuracy of the model is also increasing?
The training loss is increasing, but
I guess maybe the test loss is decreasing. I guess it's the switch between accuracy and...
The training loss is increasing, but the accuracy of the model, I don't know. I need more specifics somehow. I mean, anything can happen in principle, right? I'm sorry, but I can't.
No,
without any specific detail, I don't know.
I
mean, it's usually it's the other way around, right?
Yeah. No, I think I've actually observed this in practice as well, but I don't have an answer either what's going on. But I did notice sometimes that the training error could increase while the test error decreases. Okay, next question.
The training error could decrease while the test error increases, right?
No, the training error is increasing. Sorry.
The training error is increasing.
It's not. It's.
Yeah.
Let's maybe let's switch.
Because usually when you do optimization, training error only decreases, right?
Yes,
so you would have to be doing something slightly unusual.
Yeah, maybe let's take that question offline. How do we know huge models are not just memorizing data? How can you check that? Splitting into test and train set stops working with huge data sets because with the size of the data set, probably for every example in a test set exists a closed example in a training set.
I think this is a great question. I mean, I think my sort of rejoinder to this is like, why do you think it's bad to memorize the data? Well, first, what do you mean by memorizing, right? Like you're doing some sort of intelligence, like say you take k-nearest neighbors, right? You can say this memorizes the data, but it's okay, right? It gives you good results. So I'm not sure that memorizing the data, by memorizing, I usually separate. Okay, to me, memorizing is when you can retrieve the data, which you usually cannot retrieve the data from this. I prefer to call it interpolation, but as we've seen, interpolation is often okay. So I don't think it's necessarily bad. And I frankly, I don't have any sort of particularly useful, like what people do in practice by using validation set. I think it's fine. I don't think I have anything better to suggest for that. You just have a validation set, you look how it works with the validation set. You hope, pray that it's okay.
The next question is there a predefined number of epochs iterations after which the test curve starts decreasing again?
So the way I define it is not in terms of the iterations. I define it in terms of the number of parameters. How does number of parameters connect to the number of epochs is very unclear. It's I think this is a really hard question. I mean, the simple answer is no. The sort of more subtle answer is that not only there is no predefined number, that we don't actually have a good theoretical analysis of the connection right
now. Okay, let's do a couple more questions. So next one was, much of statistical learning theory was developed for classification. Do you think it would be possible to come up with a unifying theory for all the other approaches that are common with deepness today? Examples of supervised objectives and so on.
I hope so. I don't know about self-supervised and so on, but I think at least for classification and regression, we're kind of slowly moving toward. So I didn't make this point very sort of explicitly in the talk, but what this double descent curve does, it kind of brings parametric and non-parametric together. So that's already hints at unification. And I think regression and classification should be unified too. So yes, I think there will be much more unification in the future, but we're just, at the surface of it, we're starting to dig a little bit.
So for the next question is, what do you think about the popular belief that wide minima tend to generalize better? Moreover, how should we measure wideness of the minima?
I don't have I want to talk a little bit about optimization in a minute, but I don't have a particular opinion about like wide versus narrow minima. I think wide ones are the ones we probably find because maybe hard to find, narrow ones. But I'm not sure about minimization.
Okay, next question is, can we think about a very large model as an ensemble of overfitted solutions?
Mm-hmm. That's an excellent question. So I actually, let me just show you a picture. I skipped this, but I like that picture a lot, actually. This is something called PERT. It's a perfect ensemble of random trees. And what happens here is that if you take a bunch of trees, which fit the data each of the trees fits the data exactly. If you take each one of the trees, it generalizes pretty poorly. But when you average them, you get a interpolated classified. It's much better than any individual tree. So I think this is very similar to what's happening with big network, although it's kind of an informal connection. But yes, I think this is a useful way to think about it.
Let's do one more question and then we go back to the slides for the second half, and then we'll do more questions at the end. So the question says, is there a line of research about constructing hypothesis tests for machine learning or something comparable to classical statistics?
We don't know yet. I mean, it's all, I think that's one thing which makes it so exciting. Is that, it's like, opening like a new continent or something like terra incognita. We just don't know. It's like we have a lot of somehow observations, but
sorry, I think I lost you for a few seconds. I can hear you now, but I lost you for a few seconds. Maybe.
Okay. I was just saying this is kind of terra incognita, right? We're just like we're seeing some sort of new island, a new continent, but we don't know what's inside at all. That's why it's exciting, right? So I think that's all open questions.
Okay, let's go back to the slides and we can go back to the question at the end to see. Maybe if you can go to, if this does it, maybe you need to go, if you go into the window, you at the bottom you have resume. Okay, did you click resume?
Yeah, you can see, right? I'm just sharing my whole, so that is just, okay. Okay, so I'll proceed now, right?
Sorry, can you click resume present? Because I don't think you did. So it's.
Oh, you cannot see my screen?
I can, but it's small. So if you go into the window with the on the Google Meet, you have the resume. Yeah, if you click on that, perfect. And resume. Now it's going to be big. Okay, perfect. Now you can. Perfect. Thank you.
Okay, good. Okay, let me, okay, I guess I don't have a lot of time. So I probably have way too much stuff, but let me try to at least go over a few points. And I think here is a kind of a summary of. I think optimization is extremely important for neural networks, for modern machine learning, because everything we do now is kind of depends on this. And the reason actually is not so clear why, but the fact is everything does. And here is a big difference. You have classical optimization where there are many local minima and SGD does not converge. And you have modern optimization. And let me just point out some aspects of modern optimization, which have been analyzed by various researchers, including us. So modern optimization, by modern optimization, of course, I don't need optimization as such. I don't mean what people do now, deep networks and things like that. Every local minimum is global for parameterized networks. Okay, this is very important. Second, local methods converge to global optima. Again, this is very counterintuitive if you've seen kind of classical views on this. Third, if that small batch SGD converges as fast as GD per iteration, which gives an overwhelming computational advantage. And that's something that we've worked on, and maybe I'll describe that very briefly. And fourth, there is something which you may call essential non-convexity. It's really, really non-convex, much more non-convex in a sense than classical method. Okay, let me very briefly describe you something about SGD, because I think SGD is one key why the things work. And what is so special about SGD? Well, if you look classically at stochastic gradient descent, what does it do, right? It optimizes loss function one term at a time, or m terms at a time for a mini batch. And if you look at the classical analysis, you will see that gradient descent converges exponentially. Stochastic gradient descent converges something like 1 over t, when t is the number of iterations. And if you think about it, well, we always like exponential, right? Exponential is just so much better than anything else. Yet, nobody used gradient descent. All major neural network optimizations use stochastic gradient descent, or versions of stochastic, Adam, master of time, essentially SGD plus something. So what's going on? And let me give you a picture which I think helps to understand this a little bit. What's the reason for practical success? And the picture is the following. If you have interpolation, SGD is actually very different from non-interpolating setting. And let me explain this. So what is interpolation? Interpolation is when your constraints are satisfied. And suppose I just have 2 data points. And the first line is, so think about this plane as a space of W's. Now, when first constraint is satisfied, when I fit the first point exactly is this line. It doesn't have to be a line, it can be non-linear, but it's just simple to see it that way. And the second constraint is that line, and the target, the interpolated classifier, is when those constraints intersect, this red dot. So now you can see that if you do stochastic gradient descent, what does it do? You first move towards the first constraint, so you kind of project onto the slide, but because you don't fully project, you just move in this direction. Then you move toward the second constraint, then to the first, to the second, and so on. And what you observe is that actually 2 steps of stochastic gradient descent is roughly equivalent to 1 step of gradient descent. They both converge exponentially and essentially with the same rate. So that's what's happening on the interpolation, and that's why SGD is so effective in overparameterized systems. Now, you can actually prove, this is joint work with Sio and my drive Vasily, you can prove that you can analyze this in terms of the mini batch size dependence. But let me just kind of give you a simple idea what is happening as a function of mini batch, because this is really important. So as you're changing mini batch, what is happening is that initially you can see that when increasing the mini batch by a factor of 2, you increase the speed of convergence. So this black line is kind of the speed of convergence. So when you increase media batch by a factor of 2, you increase the speed of convergence by a factor of 2 also. So that's good. So you want to grow the media batch size. But at some point, there is some sort of what we call critical media batch size, M star. And beyond that, increasing media batch size doesn't actually help you to converge faster. It saturates. And even if you use full batch, there is no advantage. So you see, your gradient descent is kind of on the right side of right end of it, and gradient step of gradient descent is actually not any faster than the step of stochastic gradient descent with a small media batch size. You can figure out what the M star is explicitly for linear regression, at least. What does it mean? That means that in practice, this M star is often very small. It could be like, well, in some cases, it's like 6 or 10. So what does it mean? It feels like, actually, I have a specific case when it's 8. What does it mean? That means that one step of stochastic gradient descent with media batch size 8 is equivalent to one step of gradient descent with full batch. If you have 1 million data points, right, this is 8, and full gradient is 1 million. So that's how much advantage SGD gives you over gradient descent computationally. So now you can kind of see the power of interpolation and optimization, is that overparameterization allows for interpolation. Interpolation leads to very fast convergence of stochastic gradient descent. And then, of course, gradient descent maps nicely onto GPU, which is essentially parallel, well, it's like a kind of parallel computer, essentially, right? It has this, tiny little cores which can do computations in parallel, matrix multiplication. And what do you get? Well, if you think that your M is equal to 8, right, as I said before, and you have 1 million data points, then SGD on GPU will be, well, assuming GPU is about 100 times faster than CPU, SGD on GPU is 10 to the 7, approximately 10 to the 7 times faster than GD on CPU. So that means that if you use stochastic gradient descent on the GPU, you're 10 million times faster. That's an overwhelming computational advantage. That's the difference between a second and 3 months. And when you have such a large computational advantage, there is basically no way you can overcome it by having anything else. So that's that I think is like part of why, I believe at least, why deep learning has been so successful, is because the computational advantage plus modern technology with GPU parallel computation is just so overwhelming. Okay, so that's basically very briefly the advantage of SGD. But let me say something about convexity, because I think this is another really important thing which is not well understood. And I apologize, I'm kind of squeezing this in the last 2 minutes, which is, it really would require a full talk to talk about this, but at least I would like to give you some idea. So if you look at underparameterized settings, you kind of can see this classical picture, right? You have a profile of the neural network, and you have this local minima, the best parameters. And each of the things is a little bit kind of like little convex set. So if you look at the underparameterized settings, you see that locally around each minima, it's actually a convex problem. Now, when you look at overparameterized settings, the picture is like that on the right. Your minima are values. It's a whole manifold of minima. And you have, so in this case, you have this curve, this kind of sine-like curve. And the interesting thing is that what you realize once you kind of look at this is that this is essentially non-convex. So this is, by the way, joint work with Xavier Liu and Li Benju, my students. And how do you see that the thing is not convex? Well, let's just look at this profile. When you look at this, you realize that the set of minimum is actually a curved set. And if the function is convex even locally, the set of minimum has to be a straight line. It has to be an affine set. So this cannot be convex at all. So overparameterized systems are never convex, not even locally. So somehow this convex thinking really needs to be rethought. That's another thing which kind of this modern deep learning, overparameterized deep learning brings. And now the question is, what's the alternative? And it turns out that the alternative actually goes back to Pollack and Lyasevich condition. They introduced it independently around 1963. And this is a separate topic. Would take much longer to show how it applies. But basically, instead of using convexity, this is a kind of condition that we need to use for our parameterized learning. And this actually relates to things like neural tangent kernel and some recent developments. In particular, you can prove that SGD under the PL conditions also converges exponentially. I'll skip this. Okay, so now let me kind of do the final summary. So we have on the left, we have this classical model. In the classical model, careful parameter selection is required. Many non-global minima, SGD oscillates. On the right, we have this modern world. We have good generalization from inductive biases, and it's not sensitive to the number of parameters, so you don't have to actually choose this model carefully, like in the classical regimes, right? You a little bit to the right or a little bit to the left, right? You get much worse performance. You have to be careful. Here, it doesn't really matter. A little bit to the right, a little bit to the left doesn't make a huge difference. All minima are global, and you have this type of essential not convexity and fast convergence of stochastic randomness. So that's maybe this kind of overarching picture of this modern world sort of shown to us by deep learning. I don't want to say it's a deep learning world because it applies to other models as well, but it kind of has been shown to us by deep learning. And I'll stop here. I'm happy to take questions.
Perfect, amazing, thank you. This was an amazing lecture. It's definitely a lot of pointers for myself. I'll just clap on behalf of the participants for the talk. That's really good. And let me share the questions again, so we can go to them. Okay, so should be able to see them now. So I guess the top question is, why drop out and other regularization techniques work, given everything you've said? They are meant to decrease the model complexity or capacity.
That's a really good question. I think there are a couple of answers to that. Well, so all my answers should be taken, almost all my answers should be taken as conjectural answers, right? We don't know. I think it's very fair to say at this point is that nobody knows, like for sure. The things are still very new. We don't have a sort of complete theory of everything that we can answer. But we have some internal models that we can think about. And yeah, I think so. Dropout and the general regularization. Dropout is a kind of regularization, but you drop some of the weight now. Well, we don't know that regularization doesn't help. What we have shown is that it's not necessary, but yet it may still help. In particular, there is one regime where it really helps a lot when you're close to the peak. Because if you don't regularize, so if my number of features, think of it for linear regression, if the number of features close to the number of data points, I get this peak and my performance is terrible. But if I do appropriate regularization, I can still get performance there. So when I'm close to the peak, that's where regularization helps the most. Because when I'm to the left of the peak, I don't need regularization because it's already not enough features. When I'm to the right, I get good results even without regularization. But around this region, where this kind of overfitting band, that's where really it helps. And I think that many modern models may be in this regime. Again, this is conjecture, but it's not. I think that there is some evidence for it.
Cool. So for the next question, do you think models would be more robust to adversarial examples if we train them with soft labels? year labels that capture similarities between classes, for example, obtained by using the distance between classes in WordNet tree?
I am skeptical because I kind of feel that this robustness comes from the internal, the non-robustness rather, the existence of adversarial examples comes from the actual internal structure in the way we train those things. So it's very difficult to really, basically, if you want robustness, you have to sacrifice performance. It's I believe it pretty strongly.
Yeah.
You can sacrifice performance in different ways, of course. But.
I would agree with that. So the next question is, could you give us a definition of inductive bias?
A definition. I'm not sure I have a definition of inductive bias, right? That's, but I can give an example of inductive bias.
Okay.
So when we do linear regression, right, inductive bias can be related to the norm of the solution. And it is, in that case, it is our belief that small norm solutions are good. And for some models, we can prove that this is really true. But notice, this is our belief. Let me give you a related belief, actually. You take an image, right? And suppose it's an image of a dog, right? And we believe that I just change a little tiny pixel on this, just change it a little bit, it will still be a dog, right? Does it have to be true? No, it's not true. For chess, it's not true, right? If you move one piece in a chess game, you probably lost, right? If you move your queen at the if you move your queen at the where it's threatened, right? The next the one point, that it's lost. So not everything is robust to some small changes, but we believe that images are robust. That's kind of an inductive bias, and that we can encode as some sort of norm. It's some sort of a belief about the model, belief about the universe, if you wish.
So now more of a technical question. How was the norm of solution computed, the one in the kernel machine slide?
So for kernel machines, I know how to compute the norm. I just call it from the definition from the kernel machine. Now for random features, it's just a norm of linear regression. And there was a paper by Rahimi and Recht where they showed that you could approximate kernel machine by this norm. So in the limit, these two norms coincide. That's why I know that. That's why it's such a nice example, because I have the norm in the limit, which is the norm of the kernel. I can compute that. And I can independently compute the norm for the random features just by computing the normal linear regression. So it's just a usual linear norm, sum of squared of divisions.
Okay.
That's a really beautiful model. I think the random Fourier features is the best model, I think.
Okay, so there is a question that relates to my lecture, but I think it's probably harder to parse. So the question says, what do you think about the more of examples that induce gradient pointing in different directions? So I guess what I was trying to say in my lecture is that you can think of gradient descent if you look at the gradient over a mini batch as imposing this kind of tug of war dynamics, where some examples are trying to make the weight grow, and some examples are trying to make it decrease. And I was trying to go towards why you need the IID assumption. Is basically you need all or examples that represent all the modes of the data to be present, because otherwise it's like playing this game without having the opponents. And I was basically trying to explain catastrophic forgetting, and then
that's like sorry.
No, I just going back to the question. I don't know exactly how those dynamics. I don't know if you have any thoughts of that. You might not even be aware of this. I don't know.
No, actually, I have some comments on this. I think this is. I think there are two interesting things here. One is that so if you think about under-parameterized regime, right? There is a true war of examples because these conditions are not compatible. You cannot fit the first one and the second one at the same time. So when you push, the first one pushes toward this constraint, but then away from the other one. So the way to think about the war of examples is the simplest case. Well, I don't know if it's exactly technically what you use, but I kind of think about it as this. You have two parallel lines, right? This line attracts you here, the other line attracts you there. If you just start a particle here, it will just oscillate, go back and forth, right? And you never converge. What you can do some averaging and hope for the best.
Yeah.
But in this over-parameterized regime, they're somehow like this. So when you move to the first one, that doesn't prevent you from going to the second one. they're somehow complementary. They don't fight. So in the overparameterized regime, there is much less of a war. There still maybe, but it's much less common. They somehow can coexist, right? It's a peaceful world, right? There are enough features for everyone.
Cool.
You know, yeah. I grew up in the communist country, so
yeah.
so,
I mean, I guess sort of in some sense there's still interesting to think about why catastrophic forgetting still happens in extremely overparameterized models, which I think, but yeah, I don't know if there's an answer for that. Maybe that's just sort of an open question for which you don't have. Yeah.
I can maybe make one more comment about this.
Yeah.
So what can go wrong even in our underparameterized model? I think you can still have catastrophic forgetting. It's the following way, right? Imagine that I'm presenting first all examples of my one class and then all examples of the second class. Yeah. Then I'm really converging to something which I somehow don't even know this constraint exists, right? I'm just looking at the constraint from one class. And I would really converge there. And even though this don't necessarily contradict those constraints, they kind of effectively contradict them because I'm completely ignoring the fact that there is this other set of constraints that they have to satisfy. So I think something like that can still happen. Mm-hmm. Even because technically that they don't contradict each other doesn't mean that they wouldn't in practice somehow. Like when you don't see any example of the size, right? You just don't know, you have to project into this. Okay, it's very vague, but
yeah. No, I mean, this tend to be very hard to answer questions. Let's do a couple more, and then we could potentially do more questions offline after the lecture. So for the next question, it seems like there is an interesting connection between double descent and the lottery ticket hypothesis. What do you think of that? How does pruning techniques work in terms of double descent curve? Should not we go left side of the chart with pruning? Yeah, does pruning pushes us in the classical regime or not?
It's hard to say. I don't really have a sort of very crisp explanation of the lottery ticket hypothesis. It seems that yes, pruning should push us at least close to the regime, and then probably the reason that they have to do it quite carefully is probably because of the thing that you may be close to this peak, and if you don't do it correctly, somehow you mess it up. But if you do it correctly, you can probably do quite good results. But yeah, I don't know. I would rather not conjecture too much because it's getting too conjectural somehow.
Okay, so then a last question. Does the double descent phenomena suggest that we should always use the biggest network model possible? Is it the case in practice?
I have 4 letters for you, GPT-3.
Yes.
If you've seen that, well, for those of you who haven't seen it, OpenAI recently came up with a new architecture, which they call GPT-3, which has, I think, 150 billion parameters. I believe that's correct, 180, something like that, just under 200 billion. So, and they managed to train it somehow, but in any case, it works better. So it seems that from at least in practice point of view, large networks do perform better. We see this very consistently.
Yeah.
Now, is it always better? Well, we don't know, but it seems to be. It's very consistent with practice.
Cool. Thank you so much. There's still quite a few questions, so if it's okay with you, I'm gonna try to send them as
Absolutely.
for you to answer because we're running out of time. Just thank you again for the lecture. It was amazing, and thank you for being at the summer school. Thank you.
Thank you very much.